All right.
Go boy. You're like my Wi-Fi at home.
Oh, we're not on?
Do you know what your network's name? I don't think he knows about my network's name at home.
All right. So, remind me, frequency division multiplexing versus time division multiplexing. What's the difference? What does this relate to when we're talking about multiplexing? Why would we multiplex anything? Go ahead. Okay, so we can, usually it's called marshalling data, so we can marshal data from many different sources onto a single connection, onto a single wire. The example we used last time is we don't have to dig up the yard every single time we want to run a couple of more cables across campus. Okay, so then we get into different means by which we perform multiplexing. We have frequency division and we have time division. So frequency division divides up the bandwidth. We can replace the word frequency with bandwidth in this example. It divides up the available bandwidth on the channel, on the cable, among all of the connections. Okay, so if you're trying to send 10 different connections across a 100 megabit connection, each one's going to get 10 megabits of bandwidth. The alternative, time division, each connection gets the full bandwidth of the communication channel, but they only get it for a short burst of time. Okay, so we're saying time division multiplexing, and realistically, I was thinking about this after class last time, we tried to draw some comparisons between USB and serial to these. They're not really direct comparisons, but if you think about the burstiness aspect of it, time division multiplex is bursty like USB is. Because USB, any parallel technology, really deals with bursts of chunks of data that's sent on a single channel at once. It's not being multiplexed on the channel. So we're really not comparing apples to apples. But the idea of time division multiplexing performing bursty data acts a lot like USB would act, a lot like a parallel technology would act. Whereas frequency division multiplexing would give us very consistent, potentially slower, well, if you measured the fastest point in time of any of the connections, it would definitely be slower than the same communication over a time division multiplex channel. Okay, because time division, you get full bandwidth. Frequency division, you're only getting the full bandwidth if you are sharing it with nobody else. If you are multiplexing one communication channel over one communication channel, at that point, I'm not sure it's called multiplexing. But I guess technically, if you only had the very first line that you shared across campus over a fiber optic cable or something like that, when you hooked it up to the multiplexer and the multiplexer only had one input coming into it and said, okay, you want me to multiplex this across the line? There you go. I suppose that would be multiplexing, but they would get full bandwidth. Unless the person who set it up was Largen, who perhaps maybe wouldn't have changed the settings on the multiplexer. Maybe it was an 8x1 multiplexer, so he only used one of the 8 inputs, something like that.
Hey, I'm just saying.
And instead,
Time efficiency for me.
so it still divided the bandwidth up by 8, even though 7/8 of it wasn't being used. So I'm just saying that's something that somebody from Best Buy might do.
No, that's from Geek Squad. I don't deal with them fuckers.
Man, that's like super close for recording. There's like no way that microphone didn't pick that up. Oops. Ay. That was Nick Largen through number.
Hopefully Best Buy doesn't see this.
All right, so that's the idea. So these are some different mechanisms that we can send stuff, multiple connections over a single cable, and we can certainly see how that would be helpful as our networks get larger and larger, right? I mean, we don't want to have to constantly be digging up the ground between 2 points on a municipal area or a wide area network. So multiplexing is very important. Okay, we were talking about packet switching versus circuit switching last time. kind of use the example of a telephone network. Really the best example would be the early telephone network, where you actually had a human being in the middle who completed the circuit, plugged the two people into each other. So circuit switching can probably be very, very high speed for very few, small number of users, where packet switching scales to the masses. And since today we're using networks that a lot of people are on at once, scaling to the masses is preferred. So most of our networks today are packet switch networks. Our circuit switch networks are going to be very specific domains of networks, probably when you just have 2 or 3 machines all communicating with each other on a very specific time increment, where you're not dealing with randomness of human beings being entered into the equation. Okay, so punchline there is packet switching, better for multiple users. Circuit switching, better for less users. Fair enough. Okay, so kind of this is the next, kind of the continuation of that. Is packet switching the slam dunk winner? So it's great for bursty data, resource sharing, simpler. We don't have any call set up, so this is kind of talking about it in terms of the telephone network stuff. With lots of packets, we do have the idea of excessive congestion, and we see that with denial of service attacks. Most of the time that we have major internet outages here on campus, it's because we run a packet switch network that's being congested by somebody who's hitting our edge router a whole bunch of times in a very short period of time. Sending packet after packet after packet, inundating it with work it has to do with wasteful packets. Okay? So with packet switching, congestion is possible. So when we get to circuit-like behavior, and this is kind of where I was going up here, that sometimes we have hybrid types approaches with this. We like the guaranteed bandwidth of a circuit. And we kind of talked about this a little bit when we were comparing DSL to cable, right? We talked about DSL being a digital circuit. It's a dedicated bandwidth between you and the phone company, where they're providing you bandwidth up to a certain point. That doesn't mean they'll hook up enough internet bandwidth to send on that wire, but they're promising you a circuit that's capable of that. So anytime we're dealing with circuits, we should think about higher performance, guaranteed bandwidth. Bandwidth guarantees maybe for audio, video type apps, things like that. But even then, when we start talking about things like Skype, these are things that lots and lots of people are using at the same time, not a dedicated connection between here and like Ann Arbor or something like that, where we're only communicating with one destination. Let's see. So before we jump onto the next slide, do you think that packet switching is necessarily the winner? We've talked about some examples when circuit switching seems like it would have higher performance if you're comparing it directly to packet switching. When you only have, if I'm only communicating with one destination, it seems like it would be our best interest to set up a dedicated circuit between those two destinations, right? Between the two endpoints, and that would give us the most speed. But does that mean packet switching would not work in that situation? Still work, wouldn't it? Would it feel slower? So we're going to have a packet switch network between two endpoints that it makes more sense to set it up as a circuit switch, where we have a dedicated connection between those two endpoints. But instead, we're going to make it packet switched. Would it still work? Sure. Would it still seem fast? Sure. Is it going to have problems with this excessive congestion issue? If we're the only ones using it, probably not. So if we're really having a race here, fine, the circuit switch network would probably win the race. But from a human being's perspective, are they both going to seem fast? They're going to both seem fast enough? So at some point, we might say that packet switch networks cover the full gamut. We maybe lose a little performance on some specific applications, but in those specific applications when a circuit switch network might be preferred, many times a packet switch network, perhaps with some oversight, and we see this on campus, I'll talk about that in a second, perhaps with some oversight, can provide reasonable, what's called QoS, quality of service. Usually it's written as a capital Q, lowercase o, capital S, QoS, quality of service. And we've seen that here on campus. Well, you've probably seen it in lots of different places. But have you ever been using a tool on campus, been on the internet, and one thing works fine on the internet and another thing seems to be almost unusable on the internet? So for instance, maybe you're able to check your email just fine, but you can't play your Xbox because it won't connect to the network. So your initial feeling is, oh, internet's down. Well, the internet's not down. A couple different things could be going on. One thing is they are blocking the ports that Xbox Live's trying to connect on. Well, that has nothing to do with the technology the network's using, whether it's packet switched or circuit switched. They're just literally lock the door on you. They won't let you connect. But what about applications that slow way down? For instance, if we can, a lot of point-to-point networks work this way, but even BitTorrent will throttle that as well. When the data gets throttled for certain applications, so when you first start downloading something and it's originally coming down at 1.5 megabytes a second, then all of a sudden it drops to 0.5K a second. We've seen that before? When everything else seems to be working just fine. So the data, the application you're using, that data is being looked at on the network, and it has been determined that it is a low priority packet. Therefore, it will always be in the back of the line when it gets to the switches. So the switches are going to do their store and forwarding, or their routing, if you will. Not the switches, the routers. The routers are going to do their routing for the higher priority packets sooner. So, a good example would be, which network am I on right here? I'm on FalconNet, I think. Well, here, let me just switch over to ResHall. Do I have access to Eden in here? Okay, so as an example of this, I switched over to ResHall, and I happen to know, there we go. Well, I tried to switch over to ResHall. So I am on Falcon now, but Eden is available now. Let's see if I can try ResHall again. Okay, we're on ResHall. Now, I'm going to remote into a computer at my house. You'll happen to see a World of Warcraft bot, but actually it's not running right now, so you won't. You'll just see my desktop. He'd already played for 8 hours today, so I turned him off. I happen to know that ResHall does throttle Teamviewer traffic. So I'll go ahead and I'm going to log into Teamviewer. I'll remote into the machine. This is at my house. And hopefully this doesn't turn me into a liar. A lot of times what you'll see horizontal lines on the screen. So already you can tell it's loading pretty slowly, but it will actually pop up. It just becomes almost unusable on ResHall's network. The question is right now, is this a internet issue or a... Well, it actually seems to be popping up pretty quick. I would say this isn't being throttled. That's not being throttled. Typically, so let's try FalconNet then. I'm positive ResHall used to be throttled, because what I would always do is I would connect to Eden to use Teamviewer, because that was not being throttled.
FalconNet definitely throttled.
There we go. No, none of them are being throttled now. Well, so that's good news. But in any case, that protocol used to be throttled. So even though we are traveling over the same network, same physical connection here on campus, these are just different policies on these various wireless networks and also the wired networks here on campus. They're still traveling across the same wires, right? But when they go through the routers, different policies are being applied to them based on which network you were on. So certain things will get throttled, and that allows us to provide circuit-like behavior for important applications and unusable-like behavior for other applications. Make sense? And this whole net neutrality thing that's been going around, that kind of deals with the similar type of argument. Kind of the catalyst there was when Comcast throttled Netflix traffic way down. Made it kind of unusable for Comcast internet users to watch Netflix. They gave them like no bandwidth for that. Okay. Let's see. Talked about it being a network of networks. Fair enough. All right, we kind of talked about this already as well, where we have a whole bunch of internet service providers all over the world. And those guys have to get their internet from somebody, and those guys have to get their internet from somebody, and those guys have to get their internet from somebody. And then at some point you have kind of the core internet. These giant, I guess they might not be that giant, but kind of the top level important networks that are linked directly to other top level important networks that are probably regional, which can then have everybody else connecting to them, which then have everybody else connecting to them, so on and so forth. So regionally here, our next most important network is the internet backbone in Chicago, which is not one of the major ones, but from our perspective, it's the next major one. Okay, they're probably connecting to one on the maybe New York, East Coast. Okay, that would probably be one of the main entry points into the United States for the internet. And that's probably through microwaves beamed up into space and connected to another important part in Europe or something like that. Okay, makes sense? So it's a network of networks, and we rely on the networks closest to us in order to make a connection. So having said that, let's just think about this from the perspective of going on vacation. Think of it like airlines. So let's say that we are flying to Florida. We're going to go to Orlando. And there is a hurricane down there. And we're flying out of Milwaukee. Well, we could have beautiful skies here, but the flight won't take off because we can't get to our destination, right? And we kind of prefer that because you don't want to land in a hurricane. That would be, we're back to this excessive congestion possible. Store and forward. You don't want to do that with people. don't want to store and forward people. So now, what about if we are going to Florida, but we're flying there through Atlanta? Okay, so that's a pretty common thing when you're flying out of Milwaukee. That especially AirTran. AirTran goes through Atlanta for pretty much all their flights. It's their main hub. So let's say there's some sort of problem at Atlanta Airport. Everything's fine in Milwaukee. Everything's fine in Orlando. But we still can't get to Orlando because our connection on the network, the router in Atlanta, isn't allowing us to pass through. That makes sense? So we are reliant on the various steps from the Traceroute that we talked about last time. The various hops that we have to go through to get to our destination, we're reliant on all of those working. Or for those that aren't working, for them to notify whoever their parent is so that the routing algorithm can update and route people around that. So maybe instead of going through Atlanta, we're going to go through, one of the airports in Virginia or something like that. And then they're going to dump us down into Orlando. Kind of make sense? All right, so that's kind of how the internet works. Big network of networks. And we could see how this would be a mess. If we had every ISP connect to every other ISP. So if we think about this in terms of the airports again, Instead of us, if we want to fly to, we'd love it if there was direct flights everywhere, right? That's the dream from an air traveler. Okay. On paper, it sounds great that no matter where you were, there was a direct flight. But then you wouldn't be able to get flights because there would be too many airplanes going into each airport. Right? If 4,000 different airports all flew into the airport in Orlando, that would be a problem. So instead, there's like 10 airports that fly into Orlando. Make sense? So we can't have this. So it's network speak. This does not scale. Okay, we can't have every node on the network connected to every other node. We're reliant on nodes connected to a subset of every other node, and then those guys connected to a subset of every other, all the nodes, and so on and so forth. That allows us to have a cleaner connection. Okay, so this kind of gives our regional router ideas. Okay, same crap. Pretty much the same crap, except this is where they're showing the regions connecting to each other. I think we get it. Okay, so this is kind of giving the some names to the different things. When I was talking about the top level important servers, they're tier 1 ISPs. And then I suppose they're just on there. They also just put Google up there. Google just gets their own name. I don't know if this is real, but and they must just be a Google fan. Okay, but you have top level ISPs, you have your regional ISPs, and then you have the things that connect them to each other, and then you have a whole bunch of access ISPs that are at a lower level, and then you would probably have another layer below those guys. Okay, then you have Google at the top. Okay. And Google's only attached to this guy. That is weird that image just popped in my head. Well, I can, if the words come out of my mouth, it is recording friendly until if you've seen the movie, then you'll translate it, and then it's not recording friendly. Huh?
What movie?
I was just looking at this, and I kind of just started thinking about the human centipede. And if you haven't seen that movie, I wouldn't. Ay, ay, ay. All right. That's stupid. All right. So all these things are, it's stupid. We get it. The internet works like airports. Make sense? Okay. All right.
Except we don't have an airport called Google.
Okay, except there's not an air. It's Google. Well, this is the head of the centipede.
That's the head. I was thinking that's
the tail. The tail? No, this was the tail.
You couldn't get the word like butt out. I was trying to decide what it was. I couldn't get the word tail out.
Couldn't get the tail out?
Let's see. Where are we at? Okay. Delay, loss, throughput, and networks. Okay. So how do loss and delay occur? We talked a little bit about this already. You have latency issues, the amount of time it takes during the trace route. You also have store and forward issues when you have to take time to store something. That takes time. So here's one example. Packet arrival rate to a link hopefully temporarily exceeds the output link capacity. So this would be an example, kind of like what we experience here on campus. When we are expecting our router to bring back information, when we type in google.com and press enter from one of our computer labs, that's sending out a request to Google, head of the centipede, and then we're expecting a response to come back, and that response has to go through Concordia's edge router and ultimately get back to us. Well, sometimes it can't get back to us if our edge router is too busy, for instance, during a denial of service attack. And you've probably seen that happen before, where when the internet is, let's just call it flaky here on campus, and the network admins are sending out emails that were under a DDoS attack and blah blah blah, that you'll sit down on a computer and it'll almost seem like it's working for a second, or it will work once, right? You'll be able to reload a web page or something, like, oh, it's back, and then it doesn't work again. Okay, you lucked out. Okay, your packet, your response got through the router during one of the times where it was temporarily its output was not being exceeded. Okay, so this deals with kind of the upload and download speed of the router, kind of like our internet connections we were talking about, where data coming into the router is going to have, based on the cables that it's plugged into, is going to have a bandwidth max. Maximum bandwidth can flow through there. It's also going to have a bandwidth max on the output. So there's maximums on the inputs and outputs. And if there's too much stuff coming in at once, everything's going to get slowed down. And you're probably going to then also have a bunch of collisions. And actually, that's how it kind of self-corrects on networks, is things don't just kind of line up nicely because they don't have the human idea of fairness. They just all rush for the entrance, and then they just collide and destroy each other. It's kind of like Black Friday shopping. Okay? Except once again, we have stored and forward humans. So we just send them back in. Grandma took a hit. Make a copy, send her back in. All right, so they're not waiting. They all just go, collisions happen, packets get destroyed, and then they get resent by the previous link. Okay? So where you can run into problems is when you have a denial of service attack, you've basically created a whole bunch of traffic near the input of a router, for example. So anything that comes in there just gets destroyed. There's collisions. Go ahead.
Denial of service attack, but what's the second D for DDoS?
Distributed.
Yeah, typically the DDoS thing is kind of a new version of denial of service. The early denial of service attacks were usually from a single source. And it was easier to get past that. So if you've decided that you're going to write a little stupid Java program to attack the Google, okay? Like, we're going to bring down the Google, the head of the centipede. Just out of curiosity, how many of you have never seen the human centipede? Hopefully most of you. Good. Yeah. There's also a sequel.
The hours of my life that have been wasted.
Oh my gosh. This is the I need to go to chapel tomorrow. What was I talking? Oh, DDoS. Okay, so if you're writing a Java program, it's just going to open up a socket connection after a socket connection after a socket connection to Google's router. So you get their IP address or something. It's going to be pretty easy to see that there's a single an attack coming from a single IP. What they could do is just blacklist your IP address, and all of a sudden your traffic is just ignored. Make sense? So one attacker isn't a big deal. But now when we have distributed networks, or even using, the big things might be viruses, where somebody distributes a virus, a million people have this virus installed. And what does the virus say to do? Maybe it doesn't do anything horrible to your computer, but instead it instructs your computer to attack the Google. So now we have a million computers around the internet, all from different IP addresses, not even knowing that they're doing an attack on Google, but they are attacking Google. They're opening connection after connection after connection to Google. And at what point does Google say, well, these are our users. We can't just ban everybody.
They're just all trying to placate.
See what I'm saying? So that would be a distributed attack, is when it's coming from multiple. It's a swarm of centipedes. That would be the worst thing to ever see, is a swarm of human centipedes. That shouldn't happen.
One shouldn't happen.
What?
One shouldn't happen.
Yeah, one shouldn't happen. A swarm might be the third one. Okay. So
what's the solution at that point? What would Google do? Because I mean, that happened to Xbox, happened to
was the solution the swarm of human centipedes, or did we just go there? I mean, it's a good question. So
they can't blacklist everyone. They can't prevent everyone.
yeah, so you got to think about. So I mean, almost look at it from a you know, like, let's say you're a castle. So Google's the castle, and this castle is being attacked from all sides by different armies or whatever. In that particular case, even something as robust as Google can get bogged down, right? So what does Google do in this situation is they can go out and they have to look at shutting down some of the sources of those armies. Okay, so they can only fight so much right here. You know, and really their whole system is bogged down, so they can't get a word in edgewise there. That deals with the input and output bandwidths being exceeded. So what they have to do is they have to go out to the castles that are the homes of these people that are attacking, probably the next layer of routers out, and ask those routers to maybe shut or reboot their traffic. You know, either shut themselves down and restart, which then clears up a link, and if Google can then catch up, they can maybe put some, you know, it's possible what's happened is it's attacking a single IP address at Google. And what Google would do is if they can catch up and they can actually regain control of their systems, they can take that IP address offline. So all of a sudden the target's not there. Stuff like that. So it really is going to be situational depending on the nature of the attack, which is why DDoS attacks are kind of, you know, all network attacks are bad, but DDoS attacks kind of suck because there isn't just like oh, another DDoS attack solved. You really have to look at the nature of how you're being attacked and then kind of peel it back one layer at a time until you can gain access to your own systems. You know, becomes the problem. And as a network administrator, when you can't even get into your own router connected to it locally, that becomes a problem. You know, so I can, you know, so let's take Mark Newhouse as an example here on campus. If it's 3 a.m, well, he doesn't sleep here. Okay, so he's at home. And, you know, a lot of times if there's a problem, he can remote in using, you know, using Teamviewer or something like that, whatever tools he uses to remote in the network, he can remote in and do a lot of fixes without having to drive to campus. Well, during a DDoS attack, that's probably not happening. But it becomes even worse is let's say you're here on campus. So he's driven in, it's 3 a.m, he has his laptop. He actually plugs his laptop directly into the router through a serial port, something like that, and still can't access it. Because that, you know, the router is a computer, and that computer is, the CPU of it is bogged down to the point that it can't accept instructions from him locally. So what do? Well, you can restart the router. Maybe that gives you a few minutes of time before it gets bogged down again, and you can try to do whatever. So it becomes a very interesting fight to fight back against DDoSs. Yeah.
You said before that on a router you can prioritize the different packets. So you can say that yours from this computer, in case this happens, do this one first.
Well, fine, but prioritizing still has overhead. I mean, actually has more overhead. If you're going to look at every packet and say, is this one of the high priority ones? Let it through. If it's not, let's not let it through. But now, so you have a zillion low priority packets of which you have to look at each and every one of them and say, this isn't important, this isn't important, this isn't important, this isn't important. And at that point in time, nothing's getting through because your CPU's bogged down on the router because you're asking so many questions. Make sense? Yeah, I mean, it's really kind of a terrible thing. It's the example I always use in network classes is, you know, the most thankless job is the network administrator. I'm sure several of you have had, especially if you're gamers on campus, you're like, oh, Newhouse, what a jerk, blah, blah, blah. He won't open up port XYZ for me, blah, blah, blah. Well, you know, the more ports that are open, the more points of attack that our router has. And, you know, hey, if he could have every port open, he's a gamer himself. If you can have every port open for you all the time and at the same time not have to drive in at 3 a.m, he would do it. But that's just not the world we live in. So it's a very thankless job. When everything's working, you know, nobody's complaining. When it's not working, he's incompetent, doesn't know how to do his job, right? So for you IT majors that are going to go into being a network administrator or something, that's what you have to look forward to. You're either not necessary or incompetent. When everything's working smoothly, you don't even need a network administrator. It runs like clockwork. Until the human centipede shows up, and all of a sudden, you don't know what you're doing. Okay, so in any case, you exceed the input-output links on the network. So that's the interstate is backed up. Okay, that could happen. Let's see, anything else we're saying here? They're showing here that packets will queue and wait for their turn, but they're not queuing at the, well, they're talking about the output link when it has to leave the router. They'll queue in the memory of that router. But let's say that these packets are traveling along to this router, and we have this router can only take data in so quickly, and we have more packets than it's able to accept at the same time. These guys won't queue out here because this is the Wild West. There's no oversight out here on the communication link. We only have control over the packets inside the machinery, inside the routers. So all those packets are just going to bounce into each other and collide, and there's going to get corruption, and then this guy's going to have to resend them. And when he resends them, now he's getting backed up. That makes sense? So it becomes this spill-through effect as we keep going back to the router before that guy, to the router before that guy, to the router before that guy, before you start having regional internet outages. We've heard about those things before as well. Okay. So here, 4 sources of packet delay. So we have the transmission. This is when the things are lining up and they can only get sent onto the communication link so quickly. We have propagation. That's the amount of time it takes the packet to travel along the communication link to its next hop. That's not instantaneous. Fiber optic cables, it's going to travel at the speed of light. Well, it's really fast, but not infinitely fast. It takes time. Okay, especially when you consider that you've chopped your data up into a million different packets, and each of those packets has to travel along a communication link. So that's propagation delay, the amount of time it spends on the communication link. Nodal processing. That's kind of a weird way of just saying the amount of time it takes the router to process the packet. What we were talking about a few minutes ago when Mark Newhouse plugs directly into the router. Well, if he can't access it when he's plugged in directly to it, it's because the CPU is busy. That's the nodal processing. Make sense? Then we have queuing. These two are kind of related, queuing and transmission. So once you have a packet ready to get onto the communication link, that's a process to put it onto the communication link. So think about this like a roller coaster. You waited in line, you've queued for the roller coaster, now it's your turn. So they put you in the roller coaster, they put down the clampy things over your head, and they tell you you're too fat, it won't click. And then you want the guy to push on it harder, right? So it finally clicks, then you can't breathe. None of you have dealt with this. I had to wait in line for Batman the Ride 3 times. I was littler then too. So in any case, there's a process, even after you've queued up, for you to actually get onto the communication link. That takes time. All these things happen from a human being's perspective very quickly, but those things add up to some number of milliseconds, as we saw from our Traceroute examples. Okay, so for instance, here's nodal processing. What's that procedure like? So check for bit errors, determine the output link. Less than a millisecond is what they're saying. I don't even know if you can even, that's not even fair to say because it really depends on the amount of network traffic you have and that stuff. So they just threw the word typically in there just so they could have an extra bullet point, I guess. Queuing delay, time waiting as output link for at output link for transmission. That's standing in line for the roller coaster. And then depends on the congestion level of the router. Whatever. This is a roller coaster example. All right, so internet's like airports, routers are like roller coasters. This is the track, okay? Except it's not roller coasters. It's more like a train. So roller coasters would come right back to the same router, right? It's kind of a big wasted. Like usually when you get on a roller coaster, you expect to come back to the same place as you started. Like you'd be upset if you were like at the park and the roller coaster after 2 or 3 minutes, you're like 6 miles away, and you go to them hoof it, right? So yeah, so it's more like a train than a roller coaster, but you get what I'm saying.
A different roller coaster on the other side.
Why don't if roller coasters are so fast, why don't we just make all trains like roller coasters?
They do. It's called Japan.
No, those are way faster. Some of their rocket trains go like, don't they have like 250 miles an hour?
I think it's faster.
Something like that.
They have to like dim the windows so people don't get sick looking out.
I think it's faster.
Is it? It might be. It might be faster.
America just doesn't like trains.
That would be a good thrill ride. Just duct tape somebody to the front of that train.
They can peak above 300.
Imagine going for that.
That's what I was going to say. Then the GoPro. You duct tape the GoPro thing to his neck. Just point out. And then you have a little speedometer. That's in the frame. You can see it just passing 200 miles an hour. All of a sudden, his cheeks start doing that flappy thing.
And then what happens when he hits 300?
He just watches him just like silently screaming because he can't breathe it anymore.
That's true. You gotta have to get oxygen.
You die?
Huh?
You probably die.
You might die. Well, now we're right back to human centipedes.
Are we?
As soon as you said you might die, I think we came right back full circle. I guess there's multiple ways you can go. Duct tape to the front of a bullet train or participate in a horrible experiment. One of the two.
Have this conversation. I feel like I just had this conversation about bullet trains with someone.
Really?
Yeah.
I dream about this stuff pretty often. It might have been me in another class.
It did involve duct taping someone to the front of a bullet train.
Oh, it had to be me.
I
I'm the only person who thinks about that stuff. I have a problem. All right, so transmission, propagation, nodal processing, and queuing, whatever. So 3 of these things all happen in the router. So this is a router delay, and this is time between routers. So in transit, propagation delay. Oh, here, then these are the same 2 slides. They just given definitions of these.
Like, put on there very different.
Oh, I do like that. So transmission delay. This is the length of the packet itself, as well as the bandwidth, the bits per second of the transmission link. So fiber optic would be speed of light. Yeah, speed of light minus the time it takes to reflect off the walls and whatever. Fast, really fast. Yeah, this is just stupid. Propagation delay. So this is. No, see, this isn't even accurate. So we have the number of bits for the packet. This is for the transmission. Number of bits for the packet. R is the link bandwidth. Are they talking, maybe they're not talking about the bandwidth of this link, but the bandwidth between these two. That is the piece of hardware that this communication link's plugged into. How fast it can put a bit onto the communication channel. Maybe that's what it's talking about. That has a measured speed. Whatever, it doesn't matter. Just a stupid slide. Let's see. Propagation delay deals with how long the railroad track is, and then the speed in milliseconds, I guess, how fast it's. Does this say poop? No, it says prop. Man, every place I look, I see centipedes. Just
imagine a guy's face being like torn off.
That's not centipede. That's bullet train duct tape.
Yeah, I'm saying in order to not think about centipede, think about something more.
I should author my own deck of Cards Against Humanity.
Come up with an expansion after every semester.
What would you call it?
Well, actually, I have a whole bunch of me and another student have possibly sent as private messages that would not be classroom appropriate. Although I've already mentioned them as a student, so that's already inappropriate. Oh well, whatever what are you gonna do? Some of them were really funny though.
As good as forking a child in the mouth.
That happened in class.
That would have probably been last semester's theme is forking.
All right, so here we're a caravan analogy. I pretty much already talked about this, right? We've talked about interstates and this stuff, so we get this. This is all fine and dandy. Let's see if we can get through this. You're supposed now cars propagate at 1,000 kilometers an hour. From now on, you must use the word propagate when you're telling people how fast you were driving. I was propagating at 65 miles an hour down I-43. Stupid. Okay, so what do real internet delays? This comes right back to this idea of Traceroute, so we can actually see what the actual amount of time it took to get between one hop and another hop. So all those things that we talked about as delays add up to some number of milliseconds. So if I come out here and I do a Traceroute google.com. Oh, I forgot they block it, don't they?
Yeah.
ResHall might not. So there's an example of something that's being blocked. We got this. Do I have any bars? Shouldn't my phone be showing up?
It was earlier.
No. Oh well. Let me just make sure we have a good stopping point here. Oh, probe, so don't even let me go there. All right, let's just start here next time because I want to look at this is an example output of a Traceroute so we can see how those milliseconds all add up to something. I think we should be able to finish this slide. Oh,
No, you could have remoted into your computer and then Traceroute from there.
I could have, except that one's booted into Windows, not the Mac. I'd have to download a Traceroute program instead of just using it.
Still the Traceroute on.
Right from the command line?
Yeah.
Well, okay. Class is over, but if you'd like to see this as an exercise for the reader, we're
It's one of the few things that console is actually good for.
Yeah.
For
After hours go time.
Command prompt.
command prompt, whatever. If you don't use it for anything else.
We should just run a speed test on the thing and make you guys cry.
Speed test.
I'm always crying.
You're always crying.
Over my internet speed, yes.
Oh.
In relation to internet speed, yes.
Is it?
Other things, not so much.
Jeez. Is it?
The audio
It's
should be covered
it's
as present
trace
people.
and then Traceroute.
Yeah, like
Or
RT,
RT.
Yeah, instead of route. Shorthand.
So less than a millisecond, 24 milliseconds for the next hop, 8 milliseconds, 15 milliseconds, 18 milliseconds, 21, 20, or 15, 25, 20. At 15, we just got to Chicago.
Okay.
So here to here is Chicago. All right, and here's their actual,
Google?
huh?
Did you do
Google.com, yeah. So this is their actual end IP address. So you can see that we got to a tier 1 ISP and then jumped to another tier 1 ISP and then went back down the the thing to a local network here.
So Google isn't the head of the centipede.
Yeah, Google is not the head of the centipede. It is more like the tail.
Do speed test anyway.
I already closed the link.
You need to use the link.